Hello everyone, I'm Adrian, and in the following minutes I'll be presenting our novel approach on improved binary neural networks. Despite their unrivaled accuracy, running state-of-the-art models is slow and expensive in the cloud and impractical due to computational constraint and limited battery life on mobile devices. To elevate this, a popular hardware-friendly approach is network quantization, where the operands and the operations are performed using data represented on fewer bits. In this work, we'll focus on the most extreme case, network binarization, where the data is represented using a single bit. Such quantizations allows us to replace all multiplications inside the binary convolution with bitwise operations. As a result, binary convolutions are up to 64 times faster and 32 times smaller on a modern CPU, and with even higher peak performance on FPGA using custom implementations. Note that the speedups come at large drops in accuracy, and bridging the gap remains an open research question. Herein, we propose to elevate this accuracy gap from three key perspectives. We note that binary models have limited capacity, and as such, to increase it at little to no additional cost, we propose for the first time to combine and adapt conditional computing to binary networks, introducing the expert binary convolution that at runtime selects the appropriate binary expert. Then, to increase the representational capacity further, we increase the width of the binary networks while preserving the number of operations constant via grouped convolutions. Finally, we design a set of expansion directions and identify promising binary architectures. Our approach sets a new state-of-the-art on binary networks, reaching 71% top-1 accuracy on ImageNet without increasing the computational budget of a ResNet 18. Our proposed expert binary convolution consists of a gating function, a set of expert weights, and the convolution operation itself. The gating function is implemented using a small linear layer followed by a winner-takes-all activation that selects a single binary expert out of a given set. The derivative of the activation is adapted such as that all weights will receive gradients during training, even if they were not selected. On the right, for a model with 4 experts, we can see that the network developed preference for certain classes or objects evidencing the effect of multiple experts. Note that since the gating function is very light, the additional number of flops is insignificant. Unlike full precision networks, binary ones can represent a finite, relatively small number of unique combinations. To increase the information flow carried by the features, we can either increase the number of channels or the kernel size. Since the latter is dependent on the data and modeling, we focus on the former. However, since simply increasing the width will increase the computational cost too proportionally, we propose to make use of group convolution, increasing the number of groups quadratically as we increase the width. As the results show, increasing the number of channels and the group size jointly offers significant accuracy gains at no extra computational costs. Finally, we define a set of network topology directions search along the lines for an optimal configurations. Mainly, we explore the effect of the distribution of layers across different resolutions. Surprisingly, we find that this particular arrangement matters little to the final accuracy. Then we analyze wherever deeper or wider architectures are better. Given the information bottleneck, we find that deeper models are generally worse. Thirdly, we analyze how it's best to aggregate the features after a group convolution and find that an additional 1x1 binary layer is required for an optimal performance. Fourthly, we analyze how many groups should be used and how they should be distributed. Finally, we combine all of this using a semi-automatic search procedure and identify an optimal network configuration that significantly outperforms the baseline by more than 6%. As a study case, we show here a set of networks in which we vary the depth and respectively the size and distribution of the groups. Notice that increasing the depth offers diminishing returns, while increasing the number of groups to a certain point offers a good trade-off in performance. When evaluated on ImageNet, as the results show, our method significantly outperforms all prior work, including methods that use ensembles of binary networks or network architecture search-based approaches. With this, my talk concludes. I thank you for your time, and if you have any other questions, please pass by our poster session or reach out via email.